The next topic is registers. Registers are electronic components that are capable of holding large amount of data. For example, if you have a 32-bit microprocessor or a 32-bit operating system, you're typically going to have 32 registers marked 0 to 31. Each register can hold 32 bits of data. So you have 32 registers, each capable of holding 32 bits of data. And these registers are typically known as your register file. So your register file has a bank of registers marked from register 0 to register 31. Registers are constructed using D flip-flops. So D flip-flops are the electronic components. So let's construct a 4-bit register. Registers can be either parallel in, parallel out, or they can be serial in, parallel out, or they can be parallel in, serial out, or serial in, serial out. But parallel in, parallel out and serial in, parallel out are typically the most commonly used register configurations. So let us look at the parallel in, parallel out configuration. So we are going to design a 4-bit register. So 4-bit register, you have 4 flip-flops, flip-flop 3. These are all D flip-flops, flip-flop 2, flip-flop 1, and flip-flop 0. Each of them have a clock signal. So clock signal goes here, 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 and here. Each flip-flop has its own input. This is D3, this is D2, this is D1, and this is D0. Each has their own outputs, Q3, Q2, Q1, and Q0. Each of them has their own reset. So clear N, pre-N, clear N, pre-N, clear N, pre-N, and clear N, pre-N. Now depending upon how you want to set it up, whether you want the flip-flop to be reset to 0 or 1, you're going to give values for clear N and pre-N, and they are active low. So that's reset. It can go to either clear N or pre-N depending upon how you want it to reset. And then you have another input called the load input. So this is the LD input. So this load input is going to go to all these. So let's see how this works. When reset is 0, so when reset is logic 0, then FF3, FF2, FF1, and FF0 will be Q3, Q1, Q2, Q1, and Q0. It depends upon how you are setting up the reset. So let's assume that all my resets are connected to clear N. Then Q3, Q2, Q1, 0 would be 0, 0, 0, 0. And if my reset is set to pre-N, then all Q3, Q2, Q1, Q0 would be 1, 1, 1, 1. When load is 0, you have the hold operation. So no new data is going to be loaded into the flip-flop. It's just going to hold the previous value. When load is 1, your Q3, Q2, Q1, Q0 would be D3, D2, D1, and D0. So D3, D2, D1, D0, they are knocking on the door saying that they want to get stored in the flip-flop, but they are going to wait for a rising edge of the clock. So remember, all these are for a rising edge of the clock. They're going to wait for a rising edge of the clock. If at the rising edge load was 0, then those values are not going to get loaded into the flip-flop. In fact, the flip-flop is going to stay in a hold state. And if at the rising edge you have load equals to 1, then D3 goes to Q3, D2 goes to Q2, D1 goes to Q1, and D0 goes to Q0. So this is the operation of a register. Now this is a parallel in parallel out register because you can simultaneously give values D3, D2, D1 and D0, and you can also simultaneously collect Q3, Q2, Q1 and Q0. Hence it is known as a parallel in parallel out configuration.